Hello everyone, welcome back to the Topological Materials unit. You have learned in the previous classes about concepts that help you identify topological materials and their topological features of these real materials. The main difficulty in computing topological invariants is to first of all know which topological invariant to compute, and second to know all of the wave functions in the Brillouin zone to let you do this computation. But in the previous lecture, you've actually come across a counterexample, the parity criteria, which was enough to learn about how a few Bloch states transform under inversion symmetry to know whether or not that material was a topological insulator. That is, knowing the symmetry representations of the Bloch state can tell you information about the topological character of materials with enough ease that you can actually calculate this in real material settings. So now many groups have studied these ideas, but in this class we're going to focus on the constructions introduced in topological quantum chemistry in this Nature paper. For this, let us focus on a specific symmetry group. Let us focus on P6MM, which is the group of graphene that you have learned so extensively in previous classes. The Bravais lattice in this group has a few symmetries, such as translations along the A1 direction, the A2 direction. It has rotations to 180 degrees, rotations of 120 degrees, as well as two mirror symmetries along this axis and this axis. Atomic bands I defined by having an atomic limit. That is a limit where we can adiabatically separate all electrons to a single site in the unit cell. Those sites must be symmetric and they are called Wyckoff positions. The important thing about Wyckoff positions is that every single site in the position is exactly equivalent, and that means they have the same local symmetric environment and the same local site symmetry group or stabilizer group GW. So some examples of this are the triangular lattice, where we put one single site per unit cell. This is called the Wyckoff position 1A. It has the point group symmetry of C6V. That means it has all of the point symmetries of the Bravais lattice. Alternatively, we could have put the electrons on an hexagonal lattice, and that is the Wyckoff position called 2B, where 2 stands here for the fact that it appears twice in the unit cell. So this is the unit cell, and it has 2 sites in the unit cell. Now each of these sites has a different stabilizer group, and in this case is C3V. That means it does not have a two-fold rotation symmetry, but it still has this three-fold rotation symmetry. Additionally, we can also have a Kagomel lattice. Now here we will have 3 equivalent sites in the unit cell, and the site symmetry group, which will be C2V. So if they are all equivalent sites with the same symmetry group, I can now populate these sites with a given representation of that site symmetry group. So the combination of a position and the site symmetry group representation, or an orbital, defines the band representation. And these are composed of what is called elementary band representations that have irreducible site symmetry representations. So here I'm going to show you in a table a few examples of elementary band representations. So for example, an s orbital in the position 1A, an s orbital in the position 2B, and that will be in the hexagonal lattice, just like graphene. We could have a px-py doublet in the hexagonal lattice as well, or s orbitals in the 3C position. That means the Kagomel lattice. So the important thing here is that what we're seeing here in the main text of the table. This is the relationship between the real space representations given in this doublet with the momentum space representations. Of course, this is just exactly a Fourier transform, but luckily it has already been done for us, and it is tabulated in the Bilbao crystallographic server. So let us dive a little bit deeper and understand what these representations in momentum space mean. Here is the Brillouin zone of the P6M group, which has three high symmetry points. The gamma point, which has a C6V symmetry, the M point with a C2V symmetry, and the K point with a C3V symmetry. Then the representations at these momenta are going to be labeled by the little group of representations of these high symmetry points. So in the gamma point, for example, we have C6V, which has plenty of symmetries, but in particular it has two-dimensional inversion symmetry. That means we can label the representations in this high symmetry point by how they transform under parity. Particularly, there's only two representations which are odd under parity, while all the others are actually even. Additionally, in the M point, which has the little group C2V, also contains inversion symmetry. It's an additional time reversal invariant momenta, which is also inversion symmetric. And in this case, we have M3 and M4 being odd under inversion symmetry. So we can see here that in the hexagonal lattice, we have a combination of an even and an odd representation, but the total parity is actually going to be positive. When it appears that a negative parity representation is there, it always comes in pairs. And as a sanity check, we can see that all of these elementary band representations, which are by definition atomic bands, have positive parity, so they transform trivially within the parity criteria. Another point to consider is the K point, which is not a time reversal invariant momenta. However, it's a high symmetry point which allows for a two-dimensional representation K3. And one thing that we see is that if we have s orbitals in the hexagonal lattice or s orbitals in the Kagome lattice, this representation will naturally appear in the K point. That means that this will correspond to the degeneracies of the bands at the K point, touching points that will be twofold degenerate because the representation is two-dimensional. Now let's look at graphene, which is composed of pz orbitals in the hexagonal lattice, which in 2D is exactly the same as s orbitals in the hexagonal lattice, or 2B position. It is composed of two bands which are interconnected and pinned together at the K point by the two-dimensional representation. That is exactly the Dirac points that you have studied previously. If we look at the representations, we have in the lower band, we have a gamma 1, gamma 4 representation that has a negative parity and a K3 representation. But we know there is something topological about graphene. That's what we've learned in the previous lectures. So why is this? Graphene does not actually have enough electrons to fill all the two bands together. It will only have electrons filling up to the Fermi level that falls on the Dirac point. This means that there's only a partial filling of the entire band representation. Particularly in the K point, it only has electrons to fill this representation by half, because it is a two-dimensional representation with two states. So we will have a half-filled representation, and this is indicative of a symmetry and filling enforced Dirac topological semi-metal. Now, with spin-orbit coupling, we must tensor product the representations in the spinless system with the spin representation. That means we will have the double group representations. And in the K point, the K3 representation is actually going to break down into two-dimensional spinful representations. And this is what we are seeing here. This is the two different representations. So this means that actually the symmetries allow for a full gap to appear at the K point. And these symmetry representations are compatible with an insulator state. Now, if we're going to compare the specific field representations in this system with the tables that we had before and tabulated in the Bilbao crystallographic server, we're going to find something interesting, which is there is no atomic insulator that is compatible with the following symmetries: the gamma 7 at the gamma point, M5 at the M point, and K4, K5 at the K point. So this means that we know for sure that this is going to have something topological about it. So let us make a quick recap here. Topological bands are those which are not atomic bands, and therefore if we know that the symmetry representations of these bands are not compatible with any atomic band, this is a sufficient condition to know that these bands are going to be topological. So how do we go about checking the band representations if you're presented with a band structure? Let's keep with the Graphene band structure. We have two possible ways of actually finding the information about the Wyckoff position and the local representation. One way we can do is actually construct the Vanier states out of the Bloch states in this following way. This is not a unique thing. However, we will find that they will be centered at the Wyckoff position by calculating the Wilson spectrum, the Wilson loop spectrum, and we will see by acting with the symmetries of the group exactly what is the orbital representation of these Vanier functions. A much easier way of doing this is simply by looking at the band structure that you get from ab initio calculations, look at the symmetry labels, and directly compare with the tables and read out what are possible combinations of position and orbital. So in the case of graphene, both with spin-orbit coupling and without spin-orbit coupling, we know that it is not compatible with an atomic representation. And we can cross-check this with actually calculating the Wilson loop eigenvalues. Then we will see it right here. We will have these are the Wilson loop eigenvalues in two independent directions, the gamma k direction and the gamma m direction, without spin-orbit coupling and with spin-orbit coupling. In both cases, we see that it's not compatible with a single position. And we can actually see by looking at the time reversal invariant loops at k equals pi and k equals 0 that they are actually going to be located at different sites in the unit cell. In both cases, without spin-orbit coupling and with spin-orbit coupling. That means that without spin-orbit coupling, the states are composed with a combination of being on the 2b position, but also being on the 1a position. And the Wilson loop will jump from one side to the other sharply as we get to the Dirac point. This is possible because the spectrum closes. On the other hand, if we have spin-orbit coupling and we are in a fully gapped state, we will simply have some continuous spectral flow that will take us from one side to the other. So finally, let us look at the examples that you've seen in the previous lectures for real materials. For example, in bismuth selenite, which you've learned that is a topological insulator, if we'll go and check what are the symmetry representations for example, in the topological quantum chemistry website, we will find it to be a combination of a partially filling of an even and an odd symmetry spinful representation in the position 3a. That is not a unique combination. There are other possible combinations. These representations, one will come from bismuth and one will come from selenite. And we will need spin-orbit coupling to see this band inversion. So the fact that it's possible to determine just from symmetry eigenvalues that it is not an atomic insulator, it means that yes, indeed, it is symmetry indicated. Additionally, like tin tellerite, which we have seen previously, that is a topological crystalline insulator, it is in a cubic lattice, we will find that it's actually composed of a mixture between a px, py, and pz triplet located in one point of the unit cell and another one which is located in the opposite corner of the cube in the unit cell. In the same way as before, we'll see that actually, yes, it is symmetry indicated. But finally, tantalum arsenide, which you have learned that it's a vile semi-metal, if we will look only at the band representations, you will find it completely compatible with a linear combination of elementary band representations. And this means that, in fact, the topology of tantalum arsenide cannot be checked just by looking at at symmetry eigenvalues, and it is not symmetry indicated. This comes as a word of caution that this shortcut may not always be taken, and sometimes you actually need to know the entire information about the wave functions in order to know about the topology of a system. So I'll suggest you would get your hands dirty and actually go compare the tables of elementary band representations with the tables of symmetry representations of specific materials that you will find on these websites. Thank you.